All right, for this one, we've actually seen something sort of like this in the past in a problem that we did earlier. For this one, what we're really looking at is there's a couple of different ways we can look at it. The most important thing to recognize is that while there is motion in the vertical dimension, our vertical dimension, the up and down dimension, momentum is not conserved. There's a collision in the vertical dimension. The gravel that's dropped into the railroad car collides with the railroad car. But that's not the only force acting on our objects. The railroad car is experiencing an upward force from the ground, and that upward force from the ground prevents it from moving. So while there is a collision in the vertical dimension, momentum in the vertical dimension is not conserved. There's not really much we could do about that. We know that before the collision, the 4,000 kilograms of gravel is falling down. After the collision, there's no vertical motion at all. If we look in purely the horizontal dimension, though, there are no external forces on either of these carts in the direction of their motion. Now, it's possible that there's friction. We've seen enough of these, though, that it's reasonable to assume that in the short duration of the collision, there's going to be very little friction slowing these two carts down. So in the y dimension, oops, thank you, iPad. In the x dimension, momentum is conserved. All right. So what that means is that we can look just at the horizontal motion of these two things. Before the collision, the momentum of the railroad car, we'll call that object 1, is going to be its mass, 10,000 kilograms, times its velocity, 2 meters per second. The momentum of the gravel, call that object 2, is going to be its mass times its horizontal velocity, which is 0. Okay, so the total momentum before the collision is 20,000 kilogram meters per second. That means the total momentum after the collision is also, oops, that's not what I was looking for. The total momentum after the collision is also going to be 20,000 kilogram meters per second. Now, if you had access to the solvers here, and you do for this, for these practice problems, then you could plug in some numbers and you'd be good. This is a example where this is actually an inelastic collision because these two objects stick together after the collision. And that's not because of the nature of the materials, that's because the collision itself is occurring in the y dimension. The actual force between the objects is occurring in the y dimension, the force that we're looking at. And so in this case, these two objects stick together, so you check the little box that says that it is a inelastic collision. We can also solve this using algebra. After the collision, the mass of the cart times its velocity plus the mass of the gravel plus its velocity should equal our total momentum, which we know is 20,000 kilogram meters per second. What we're trying to find is the velocity. Both of these objects are going to have the same velocity, so we can factor that out. Our velocity after the collision times the combined masses is going to be equal to the momentum after the collision. That means our final velocity is going to be the momentum divided by the combined mass of our two objects. That's going to be 20,000 kilogram meters per second divided by the combined mass of 14,000 kilograms. And that's whatever that is. We'll figure that out, and that would give us our velocity in meters per second.